We're going to finish up L'Hopital's rule, and we're going to go to example number 8. I'll go back to 7 in a minute. First thing I want you to notice about this one is that if we plug the infinity in, we get infinity to the 0 power, which, while it is one of our indeterminate forms, it is not the setting that we need for L'Hopital's rule. What we need for L'Hopital's rule is either 0 over 0 or infinity over infinity, which means we need a fraction in the base. Here's how we're going to get that. First thing you're going to do is you're going to define the answer as L for limit. The second thing you're going to do is you're going to take the natural log of both sides of this expression. Now, why do we do that? Answer. If we do, using the power rule, we can take this exponent and we can bring it in front. When we bring this exponent in front, and we're left over with this natural log of x, can you see that we now have a numerator and a denominator? The numerator is approaching infinity, the denominator is approaching infinity. We have infinity over infinity. Those are the conditions for L'Hopital's rule, and woo, it's time to take it to the hospital. The derivative of the numerator is 12 times 1 over x. The derivative of the denominator is 4. Now if we take the infinity and plug it in, we get 12 over infinity divided by 4. 12 over infinity is 0, so the whole expression is 0. Now that seemed easy enough, but what you need to remember is that 0 is not actually our answer. 0 is, look back up here, equal to the natural log of the answer. So I'm going to write down the natural log of our answer is 0, and if we exponentiate both sides, we get that the limit is equal to e to the 0, which is 1. 1 is our actual answer. Let's take a look at another example. I'm going to go back to number 7 now. In number 7, we have the same game. We plug in the infinity, and what we end up with is 1 to the infinity, which is not the form we need for L'Hopital. Anytime you have this situation and you have an exponent, I want you to call the other side L, and then take the natural log of both sides. What that does is it allows us to take this exponent right here and bring it in front. Now I know what you're thinking. You're thinking, Mr. Klein, even after I bring that n in front, what I have here is infinity times 0. And infinity times 0 is not the format for L'Hopital either. So you need to do one more rewrite. We need a fraction, and here's how you're going to get it. See that n right there? You're going to move it to the denominator. When you move that n to the denominator, we now have this, 1 over n. See how I flipped it when I moved it down here? Which means that the numerator is going to the natural log of 1 plus 1 over infinity, which is the natural log of 1, which is, you guessed it, 0. And the denominator is going to 1 over infinity, which is 0. Woo, woo. Time to take it to the hospital. So the limit as n goes to infinity is going to be equal to, in the denominator, I'm going to call this n to the negative 1, which makes the derivative negative 1 times n to the negative 2. In the numerator, I'm going to call this 1 over 1 plus 1 over n multiplied by the derivative of the inner function, which is 0 plus That's the same as this. So we get another negative 1 times n to the negative 2. And then you say to yourself, I can cancel both of those, which leaves us with 1 over 1 plus 1 divided by infinity, which is equal to 1 plus, or 1 divided by 1 plus 0, which gives us a 1. And here, once again, you want to be careful. The answer is not going to be 1. The answer is going to be the natural log of L equals 1. So if we exponentiate both sides, we end up with the limit being equal to e.